This video will introduce you to how to calculate capacitance for a few different capacitor geometries. We'll start out with the general method, following along with 4 steps. For starters, we're going to assume that there's a charge of Q on each plate. As we know, one of those plates will be positive and one will be negative. And again, we're using the word plate to mean conductor in this case. We're going to then derive an equation for the electric field between the plates in terms of Q, and we're going to do so using Gauss's law. So we're really going to focus on finding capacitance for capacitors with some good geometry. And then, knowing that electric field, we'll derive an equation for the potential difference between the plates, using the fact that the potential difference is equal to the negative integral of E dot ds. And lastly, we'll use our equation for capacitance, which is that C is Q over V, to determine the capacitance of our capacitor. Let's try it out with probably the simplest version first, which is calculating the capacitance of a parallel plate capacitor. And we're going to say that plate area is capital A, and the distance between the two plates is lowercase d. In other words, just kind of drawing that distance out. This distance right here is what we're calling d. Now, I've already included some markings of what the charges would be in this case. And we don't even really have to, or in this case, we're assuming that it's a Q on the top plate, Q on the bottom plate. So let's jump right into using Gauss's law. We know that the first thing we have to do when using Gauss's law is to choose a Gaussian surface. And in this case, I'm going to choose a Gaussian surface that encloses all of the charge on the positive plate. The best Gaussian surface in this case is going to be kind of a rectangular prism, I guess you could say. A cube, but not with equal sides, really. And I'm going to purposefully make my Gaussian surface so that one part of the surface actually lies within the conductor. This now encloses all of the charge on one of the plates. I would not want to enclose all of the charge on both plates because we know that I'd be enclosing 0 charge, and so I'd get 0 electric field. And we know that that can't be accurate because we know that there is an electric field between the two plates. For a fact, if I were to draw that electric field, I know that electric fields start on positive plates, or start on positive charges and end on negative charges. And you may recall from that lab that you did that the electric field in between the two parallel plates is actually fairly uniform. In other words, it's all the same direction and it has all the same magnitude. That'll make using Gauss's law relatively easy. Let's write out Gauss's law. We know that Gauss's law is the surface integral of E dot dA, and that equals Q enclosed for epsilon naught. And we know that for the bottom face only, that E is parallel to dA. And so we can get rid of that. Luckily, for all of our other faces, E is either 0, that would be true of the top face since it's inside of a conductor, and for the other 2 faces, or really the other 4 faces, the area is perpendicular to the electric field. So we really only need to focus on that bottom face. We've already talked about the fact that the electric field is constant in between those plates. That tells me that I can pull that E out of my integral. And since I'm left with the area of just one of my faces on my Gaussian surface, I just have E times A. Now, thanks to the way that I made my Gaussian surface, this A of my Gaussian is equal to the plate area, A, that was given to me in the problem. That's convenient because that means that I don't have to write any new expression for A. I'm allowed to leave it in there. We also know that the charge on one of the plates was just Q, and I enclosed that entire charge. So that tells me that I can just put that as a Q in the numerator, and it's Q over epsilon naught times the plate area A. We have now completed that second step of calculating the capacitance. So we get to move on to the third step, which is coming up with an expression for the potential difference between the two plates. So we're going to use the fact that we know that the potential difference, delta V, is equal to the negative integral of E dot ds. And I'm going to move, I'm thinking about that potential difference. We think about moving in a certain direction, right? Because we're looking at the potential difference between 2 points. And in this case, I want the potential difference between the faces of the two plates. And so I'm going to move in a straight line, and I'm going to move from this negative plate up to that positive plate there. And so that means that the dot product, as I'm doing the E dot ds, the angle between E and that ds would be 180 degrees. And we know that the cosine of 180 is -1. So that means that that negative cancels out with the negative that's out in front of my integral. And then I just have E ds. Luckily, we also know that the electric field between the two plates is a constant. So I can pull that out. Then I have the integral of ds. And that's just E times the distance I moved. And in this case, the distance I moved was D. So putting this all together, delta V is E times D, and E is Q times divided by epsilon naught times A. So that means that delta V is equal to Q times D over epsilon naught times A. Then I get to move on to my last step, which in my opinion is actually the easiest of all 4 steps, or maybe second easiest beyond step 1, and that's actually calculating the capacitance. We know C is Q over delta V, but instead of using a capital Q, I kind of assumed that the charge here was a lowercase q, so being consistent, we'll say a lowercase q here. And that means that I have Q divided by this fraction, and of course when I have a fraction in there, it's like I multiply by its reciprocal. And since I have a Q in the numerator and a Q in the denominator, I find that the capacitance is equal to epsilon naught times the area of the plate divided by the distance between the two plates. Now, here's the deal, something that's actually really fortunate. 2 things actually. First of all, this equation, C equals epsilon naught A over D, is on your equation sheet. So even though it's on your equation sheet, you still must know how to derive it, because that was one of the learning objectives set aside by the College Board. So make sure that you know this process. Another thing that makes this a bit simpler than it could otherwise be is the fact that the electric field in between these two plates is constant. That means that we don't have to use the superposition principle to be able to find the electric field from one plate and then the electric field from another. So again, just looking over this method, we used Gauss's law to find the electric field, an expression for the electric field. Then we used the fact that the potential difference is equal to negative integral of E dot ds to find an expression for the potential difference between the two plates. Then we plug that expression into our equation for capacitance to find an equation for the overall capacitance of our parallel plate capacitor. In class, we'll see examples of using this process with a cylindrical capacitor as well as with a spherical capacitor.